So as I was saying, Unit 14, this is your last unit before your final. It's all based upon probabilities. Some of this you have had before, some of it you have not. Some of you haven't had any of it. It depends on who your teacher was, but you should have had some of this. So we're going to start with counting outcomes. So in probability, it's really important that you know how many possibilities there are for an event to happen. In other words, if I said, what is the probability of you earning an A on yesterday's test? We'd have to know how many answer choices there were possible for you. Let's say it was multiple choice. Some of it was multiple choice, right? So you could have known absolutely nothing on the test, and you could have guessed and gotten some questions correct, couldn't you? So if you have a multiple choice question with 5 options, A, B, C, D, E, how many choice answer possibilities are there? A, B, C, D, E. 5. How many correct answers are there? 1. There should be 1 correct answer. So what we're counting right now are all those 5 outcomes. So on that one, that's easy. When you roll a die, 1 number die, how many outcomes are there on 1 die? 6. But what you're going to have to figure out is how many outcomes there are on 2 dice. So a pair of dice. I mean, who knows? I heard it. 36. And I'll show you how to figure that out shortly. If we're flipping a coin, how many outcomes are on a coin? 2. Heads or tails, right? So those are the types of things that we're going to look at today. And then we're going to take that and figure out, well, if now that we know the whole sample space, all the possibilities that you could have, what's the probability of this particular event occurring? And so we'll go into that later. So for right now, here's your first example. At football games, see if I can blow this up. And again, for these watching the video, my document camera is very dim today, sorry. So at football games, a student concession stand sells sandwiches on either wheat or rye bread. So there's a choice. I have a choice of either wheat or rye bread. I can't have both. The sandwiches come with salami, turkey, or ham. So those are 3 choices. And then either chips, a brownie, or fruit. If your mother's buying it for you, she's going to buy you fruit. If you're buying it, what are you going to buy? Chips or a brownie? Most of you aren't going to. Some of you will choose fruit. All right, so then the directions specifically say use a tree diagram to determine the number of possible outcomes. I could actually tell you the total possible outcomes without using a tree diagram, and we'll do that in a minute, but it's physically saying use a tree diagram. And oftentimes, if it doesn't say use a tree diagram, the directions would say list out all the possible outcomes. There's a difference in the directions saying list out the possible outcomes versus how many possible outcomes there are. So we're going to list them out, and I'm going to show you how to find the total possible outcomes without listing them. You just won't know what they are individually. So when you have choices, you're going to take your choices and put your choices as columns going across. So what's your first choice? Bread type. So your first choice is bread type. By the way, you might be doing something, instead of choosing items to go in your sandwich, you could be choosing, you could be flipping a coin, spinning a spinner, and rolling a die. Those could be your 3 different events that are occurring. Each of those would be flipping a coin. What are the outcomes on a coin? Heads or tails. Spinning a spinner, your outcomes might be red, blue, and green, so you'd have 3 different outcomes. And then rolling a die, how many outcomes again on a die? 6. So you'd have like 6 outcomes there. And then each of those are branching. So with your bread, you have 2 outcomes. We have either wheat or rye. So I'm going to use a W and an R, and you want to space them out fairly far because you're going to have branches coming off of them. And then your second choice is your meat choice, right? So type of meat. And we've got salami, turkey, or ham. So if you choose white bread, you're going to have those 3 choices, salami, turkey, or ham. If you choose rye bread, you're going to have the same 3 choices, salami, turkey, or ham. And then what's your third choice? So I would say dessert choice, so type of dessert. Each of these choices have 3 dessert types, don't they? So off of the salami comes 1, 2, 3. Off the turkey, 1, 2, 3. Off of the ham, 1, 2, 3. And each of these would be chips, brownie, fruit. Chips, brownie, fruit. Chips, brownie, fruit. And then same thing down here. 3 choices here, 3 here, and 3 here. Chips, brownie, fruit, chips, brownie, fruit, chips, brownie, fruit. And then what you need to do to finish this up is list out your final choice. So you can't leave the tree diagram as is. So your final choice, let me run back here, or you might say combo. They use the combo meal a lot in fast food restaurants. So I would have wheat, salami, chips, or wheat, salami, brownie, wheat, salami, fruit, or wheat, turkey, chips, wheat, turkey, brownie, wheat, turkey, fruit, wheat, ham, chips, wheat, ham, brownie, wheat, ham, fruit, and so forth, right? And so do that all the way down. I'm not going to talk. I'm going to let you figure it out. How many choices here with the white bread? How many choices total? 9. How many choices with the rye bread? 9. So how many choices altogether? 18. So 18 combos total. Now, if that's all they wanted was just the total number of combos, I would never do a tree diagram. Wasn't it a pain in the butt? But if they asked me to list all the different combos, I kind of need to do the tree diagram. I really do, because otherwise some of you are going to miss it, especially if I do something more complicated than this. Otherwise, if they were just asking for the total number of outcomes, I can use something called the counting principle. So the counting principle says this: multiply your choices together. So how many choices for bread did we have?
2.
2. Times how many choices for meat?
3.
3. And how many choices for dessert? 3. What's 2 times 3?
6.
And 6 times 3? So 18. So doesn't it match the 18 combos that we listed out? So that's the quick way to do it. If that's all I want is the total number, I wouldn't want to go through all the effort of a tree diagram. Why not just use the counting principle? Okay. So then some simple probability that we're going to get into, I'm just going to start you on it right now today, would be, so put here simple probability. Simple probability is just favorable over total possible outcomes. So we've got number of favorable, meaning what do you want to occur? So number of favorable outcomes divided by total possible, bless you, outcomes. So I might ask you the following question. What is the probability that a meal combo will have a brownie? So let's put here probability of a brownie. So this is shorthand for probability of a brownie. How many meal combos have a brownie in them?
6.
So let's highlight them. So we've got these 3 right here, correct? And these 3 right here. So we do have 6 total. Those are our favorable out of how many total possible? 18. So doesn't that reduce to what? 1 in 3. So don't we have a 30? We have a 1 in 3 chance. That's a 1 in 3. So we have a 1 in 3 chance or a 33% chance. Didn't I ask for backpacks and purses to be on the floor? So I want all backpacks, all purses, all big notebooks on the floor. That includes yours, Thomas, yes. So that's generally what we're going to end up doing with that. And would I have been able to figure out the probability of which combos have a brownie in it if I didn't do the tree diagram? It would be harder, wouldn't it? So that's the tree diagram has its uses so that I can see all the different combinations necessary. All right, so let's look at example 2. So the Two Computer Company sells custom-made personal computers. Customers have a choice of 11 different hard drives, 6 different keyboards, 4 different mice, and 4 different monitors. How many different? And here's the question: how many different custom computers can you order? Are they asking you for a list? Use a tissue. Are they asking you for a list of the different outcomes, or are they asking you for just the total outcomes? Just the total, right? So what are you going to use? The counting principle or a tree diagram?
Tree diagram.
Counting principle. If all you need is just a total number, then use counting principle. So you go ahead and try that. See how you do. You have your choices. Just multiply them together. All right, so some of you are going, I don't have a calculator. I can't possibly multiply that together. Yes, you can. What's 11 times 6? 66. What's 4 times 4? 16. So all I did was break that up into things that I know how to multiply. And then can't you just do one multiplication, 66 times 16? So if you didn't have a calculator, yes, you could. And that turns out to be 1,056 total custom computers. All right, so flip that to the back. All right, so example 3. There are 8 students in the algebra club at Horizon High School. Because it's such a popular club, there's only 8 of them in there. The students want to stand in line for their yearbook picture, and because they're in the math club, they need to figure out before they actually stand in line how many different possible ways could the 8 students stand in line.
Hey,
because they're math students. So I have 1, 2, 3, 4, 5, 6, 7, 8 places in line, don't I? This would represent the first, second, third, fourth, fifth, sixth, seventh, and 8th. Thank you. So let me ask you this. How many possible...
No more excuses.
Good Lord, that scared the bejeebers out of me. This is why we don't usually have the door open. All right, so how many possible students could I place in the first slot here? 8. There are 8 total, right? Well, I put 1 person in that spot, don't I?
Yeah.
Yes.
And just multiply 8 times.
Okay, can I stop you for a minute? Because I'm teaching. Okay. So then I put 1 person in that spot, right? Do I? Right? Mm-hmm. Yes. So then how many are available for the second spot?
7.
7. And I put a person on that spot. So now how many are available
6.
for the third? 5, 4, 3, 2, 1.
I knew it.
Is this story, if I change the story and say I'm aligning books in a row, or arranging books in a row, would it change how I do this? Or arranging CDs in my CD holder, would it change? It doesn't matter what I'm arranging. If I'm arranging them in order, then only 1 can go on each spot. And then we will multiply each of these possibilities together, because if I did a tree diagram, which we're not, but I would have 8 choices for my first spot. Then depending upon which person is standing there, I would have 6 choices attached to each of those 8 people, right? for the second spot, and then it would become this huge tree diagram, wouldn't it? Well, this thing is called a factorial. It's actually equal to 8 exclamation point, and that's called 8 factorial. 8 factorial. All right, and notice that for 8 factorial, what do we start with? 8. And we multiplied by 1 less every time until we got to 1. And so we're going to go ahead, I'd actually let you use your calculator for that. I do expect you to be able to do a factorial below 10 by hand. It's possible. But I will let you know what that is. So if I multiply that all together, we would actually have 40,320 ways that those little algebra math students could line up. That's a lot of different possibilities. We want 40,320 pictures just to prove that it's true. Can you imagine? Expensive, but true. Well, I guess not so expensive as if it's digital. All right. Then I'm going to ask you, I'm going to pose this question to you. How many ways, write this down, how many ways can the club elect, oh, there needs to be the word can the club elect a president, vice president, and secretary? I'm having trouble spelling today. So how many ways can the club elect a president, vice president, and secretary? Anybody can be president. Didn't your mommy tell you that? So, again, how many possibilities do I have for choices? How many choices do I have?
5.
Are you listening? Is everybody listening?
3.
I have president, vice president, secretary. So one choice is for pres. One choice is for VP. Another choice is for secretary. Again, we will multiply each of these possibilities together. How many people could run for president?
8.
8. Wouldn't one of them be presidents?
7 and 6.
And then there'd be 7 for vice president, somebody would be VP, and then there'd be 8 available for secretary. So then multiply, or not 8, 6. Thank you. So then multiply 8 times 7 is 56. 56 times 6, that will give you 336 ways that those elected offices could be chosen. Now this is no different than if we had a race. If we had 8 people in a race, how many ways can they finish first, second, and third? Wouldn't I do the very same thing? Only one person can finish first, 8. Only one person can finish second, 7. And only one person can finish third, 6. Now that's not to say that there couldn't be a tie, right? We won't go into ties. Typically, if there's a tie for second, do you ever give a third place out? No. Mm-mm. You get 1 first place and 2 second places, that there is no third place. Yeah. All right. So then, I want you to find the value of 9 factorial. Write it out first of all, and I'll show you the shortcut. But write it out first. Stop talking. TJ, turn around and do what I asked you to do on your own paper. That's what 9 factorial looks like, correct? What's this right here?
40,000 something.
But that's your 8 factorial, right? Which TJ's right. So you're going to take your 9 and multiply it to, you already found 8 factorial above, so as you're doing your work, shorten up your work and go, oh yeah, I already found 8 factorial, it was 40,320. So you multiply 9 to that. That should be fairly simple. And then tell me what you get. What'd you get? 362,880. Okay. So that's one way that you can shorten things up if you know part of the factorial because you've done it before. Heads are off the desk. I know it's hot, but heads are off the desk. If you lay on your desk, chests are off the desks. You are to sit up straight because if you slouch, we've had this conversation before, what happens to your diaphragm?
You'll break your back.
No. If you slouch, you're scrunching your diaphragm, and then less air is getting into your lungs, which less air gets into your brain. And what happens when people don't have oxygen to the brain?
They die.
No, they get sleepy, and then they die. But you're not going to die in here. You pass out asleep first, which is what some of you do. So sit up straight, Jacob.
Forward brings more blood to this little right here.
No.
I don't know what it's called, but
No.
Little brain.
All right, then this is something that you're going to talk about more about factorials tomorrow. But let's see if you can remember this tomorrow. 0 factorial. You write down silently what you think it equals. So, silently, what you think it equals. What do you think it is?
0.
You're wrong. It is 1. It is 1 because let's just use a simple factorial. I'll just use 3 factorial, for instance. If I had 3 factorial divided by 3 factorial, what's anything divided by itself? 1, okay? But that would be 3 factorial over 3 factorial. And technically that's the first power, isn't it? Well, technically. What's 1 minus 1? 0. And haven't we had discussion that anything to the 0 power is 1? Well, 0 factorial is also 1. Because all of those cancel. 1 factorial is also 1.
That's not possible.
Yes, it is possible. All right, so remember that because that's on your test. And 50% of you are going to get it wrong. Ha, what's the probability of that? 50%.
50%.
Okay. No, I'm just warning you. I warn you all the time and you all don't listen. If I had a teacher that said 50% of you fail this on the test, what would I be doing? I'd be going like this. Oh my gosh, I'm not missing that. So I'm going to go and I'm going to review that before my test. But that would be me. That's not all of you. Some of you never look at these notes ever again. Okay. Now, last example. Jill and you should know how to do this now. Jill and Miranda are going to the Grand Canyon for their vacation. Near the campground where they are staying, there are 8 hiking trails. Okay? Part A, I want you to figure out how many different ways they can hike all the trails if they hike each trail only once. Silently to yourself, figure out all the ways that they can. In other words, for their first trail hike, how many choices do they have? For their second trail hike, how many choices do they have? For their third trail hike, how many choices do they have? So silently write that down. You should have the answer right now. Silently. But you should still show your work. Quit talking. This is your last chance or you're gone. Mm-hmm. Yes. Yes, it's not 216. Thank you for asking. What'd you get? A number?
A lot of numbers.
What number? Right, because how many choices do you have for your first hike?
Forwards and backwards.
There's 8 trails, so you have 8 choices.
Oh.
And then for your second hike, because you're only doing each one once, 7 choices, 6, 5, 4, 3, 2, and 1. So wasn't that our 8 factorial again? Okay, so that is 40,320 ways, right? All right, then do B. This one you're going to actually have to do some thought. So if they have only time to hike on 5 of the trails, how many ways can they do this? They only have time to hike on 5 trails, and you're going to assume that they're not going to hike on, you know, the same trail 5 times. So 5 different trails. What factorial is this?
5.
It would be 5 factorial because they have, well, no, it's actually not 5 factorial. They have 8 possibilities for the first hike, right?
Mhm.
They have 7 for the second, 6 for the third, 5 for the fourth, and 4 for the fifth. And then you stop there because it's almost like asking if there's 5 place finishers in a race and you have 8 racers, right? How many different ways could they finish? So you need to multiply those numbers together.
7.
So get smart and multiply things that you know that you can multiply easily together. So, like you can,
7 is 56. 6 times 5 is 30.
yep, so there's your 56. And then you could go 6 times 5 is 30, right? And then what's 30 times 4? 120. So then all you have to do is 56 times 120. So I don't have to have a calculator. And I get 6,720 ways.
Yes.
All right, so then I'm going to pass out to your homework. Now, even though I do assume that you are going to use a calculator when you're doing something like this problem, do I expect you to show work? Absolutely. If I see none of this written out, like how did you come up with that number, you just have a number slapped down, you pass that over to TJ, then I'm just going to say, well, you copied everything off of my website, it's a list of answers, no credit for your work, so be careful. Pass that over to Mike. That's for you. Jack. Okay. So let me just bring your attention to the directions. For 1 through 3, what do the directions say? Construct a tree diagram. Well, we're not going to do that here, so I just want to remind you that for 1 and 2, you're constructing a tree diagram. There's a reason why there's some space there, so write small. And then there's some questions here based upon some simple probability that you ought to be able to answer. Favorable over total possible. Then you're going to use your counting principle for this one. Oh, and by the way, this should be, Mrs. Baker's messed up on her numbering. This should be through 16. So you're going to use the counting principle. So let's look at number 3. I want you to use your counting principle for number 3. So this says how many different outcomes can result from flipping a coin 4 times. You have how many events? How many events are occurring? 4 events. Each of the coin flipping is 4 events. So for your first event, here's 1, 2, 3, 4. So you're going to take your 4 events. This is your first, your second, your third, and your fourth. And you're going to multiply those probabilities together. How many different outcomes are there on flipping a coin? 2. So we have 2 times 2 times 2 times 2. What does that give you?
16.
16 ways. But look at number 4. My fiance's family has 2 girls and 1 boy. The order is girl, girl, boy. How many possibilities are there for a family with 3 children? So again, you have how many outcomes or how many events? Each birth is an event, assuming that we don't have twins. We just have single births. So we have 3 births. So this is the first child. This is the second child. This is the third child. Times and times. How many possibilities for children can I have? Two, a male and a female, right? A boy and a girl. So 2 times 2 times 2. So what do you get? 8 possibilities. So 8 possibilities. All right, so then flip to number 8. This time it says using the digits 1 through 9, so we don't get to use 0. How many different 4-digit numbers can be made if you can repeat digits? There's a difference between repeating and not repeating digits. So how many events do I have occurring? I have a 4-digit number. Each of those digits is considered an event because I can choose numbers for each of those digits, right? So this is the first digit, the second digit, the third digit, and the fourth digit. I'm going to multiply those possibilities together. But this time it says I can repeat digits. So I can have 9999, 2222. So how many choices do I have for the first number? 1 through 9? 9. What if it were 0 through 9?
9.
Then there'd be 10. 10. If they just said, how many possibilities are there for a 4-digit number, and they don't mention anything about 1 through 9, you assume it's 0 through 9, and then you would be putting a 10 there. And so don't we have 9 for the second one, 9 for the third one, and 9 for the fourth, because I can repeat numbers? What's 9 times 9? And then that one would be 81. Wouldn't you be doing 81 times 81? And that gives us 6,500, thank you, 61 different numbers. Make sure you put a box around your answer. Bless you! And again! She sneezes a million times. All right, look at 13. A 6-sided die is rolled twice. You're not rolling 2 dice. You're rolling one 6-sided die twice. So we're looking at this one. How many different outcomes are possible? So how many events do you have occurring? 2 events. Here's the first, and here's the second. Times. How many possibilities for the first event?
6.
6. And the second?
6.
6. So we have 36 outcomes. Is that any different than rolling 2 dice at once? No. Rolling them separately or at once will make no difference. All right, then, oh, by the way, because we have a second question here, don't we? What is the probability that you roll the same number twice? Okay, so we have to think out of those 36 outcomes. So again, we're going to do favorable. Well, we could do it 2 different ways. We could do it 2 different ways. But it'll be interesting. We could do total favorable, or all favorable over total. So could I roll a 1 and then a 1? So that's 1 favorable. And a 2 and a 2? 3 and a 3? 4 and a 4? 5 and a 5? And a 6 and a 6. How many total is that?
6.
So I would have 6 out of how many total possibilities? 36. Does that reduce? 1 in 6, right? Or, think of it this way. I only have 1, let's say I want to roll, each number only has 1 chance of coming up on each die, correct? Once. So if, on the first roll, I would have a 1 in 6 chance, wouldn't I? Well, actually, it doesn't matter what I roll on the first one. 6 possibilities on the first one, because it wouldn't really matter if I roll a 1 through a 6, right? It doesn't matter what I roll on the first one. I have 6 favorable outcomes. But it does matter what I roll on the second one, doesn't it? On the second one, no matter what's rolled here, I only have 1 matching number on the second one out of 6 possible numbers. Does that make sense? For the first roll, it doesn't matter what I roll. I can roll 1 through 6. So I have 6 favorable outcomes. But on the second roll, I will only have one number on that second roll that will match what came up on the first roll. And so I only have one favorable. Don't these 6s cancel? And would that still leave me with a 1 in 6 possibility? So either way that you look at it, you'll still get a 1 in 6. I think it's easier to look at it this way, but you can't always look at it this way. It depends on what the question's asking. And then you might want to put another little line through here because you really have 4 separate problems here. So if you look at this, you really have 4 separate problems. And then this problem should be problem 16. That's 13, 14, this is 15. And then this is 16. All right, that's all I'm going to go over with you. Any other questions? Okay.